All right. Thank you, Luke, for the opportunity to present the work here. As Luke said, this work I'm going to present came out of a model intercomparison project called COVID-MIP. So all the simulations were required to finish in less than 3 months. So we got it done by end of September. And I particularly want to thank Minxuan Wu, who is currently a postdoc working with me at PNL. He has done all of the E3SM simulations and analysis for this work. Without slowing down his major aerosol development task for the E3SM V3, he did sacrifice many nights and weekends babysitting all the simulations. And also my former postdoc, Yang, who is now a professor at the Nanjing University of Information Science and Technology. And his graduate student, Lili Ren, also participated in the intercomparison, but with CESM1 model. And we coordinated all the simulations and cross-checked our emission data sets and test simulations to try to avoid any mistakes that we cannot afford of. And Kate also is a key contributor to this work. And beyond the author list here, I also wish to thank Susanna, Philip, Ellen, Matthew, and Shoyin for their help in preparing some model input files. And also, of course, many others on the E3SM project team for making the model available. And finally, the EESM program for funding support. So the worldwide dramatic responses to the COVID-19 pandemic started with China's national-wide lockdown in late January of 2020, have led to large reductions in human activities, and therefore the emissions of greenhouse gases and aerosols are also largely reduced. So this figure on the left shows the global emission reductions in primary aerosols and precursor gases, as well as greenhouse gases, estimated from mobility data from February to June 2020. So all those reductions have triggered lots of research interest in environmental and climate sciences community. We try to understand the impacts of this emission reductions. So many studies published in 2020 have shown discernible impacts on regional air quality and climate. For example, based on a simple energy balance model, Forster et al., they found short-term cooling associated with less greenhouse gases compared to the baseline, and warming due to less aerosols. And by prescribing aerosol emission changes during 3 different phases, lockdown, back to work, and post-lockdown stages, so Yang et al. Showed a surface warming effect over major continental regions of the northern hemisphere via aerosol radiation and aerosol cloud interactions. Then the question is, how about the Yang et al. Simulations use the AMIP type prescribed SST and CIs. So the question was how the climate, how about climate responses involving the slower oceanic processes and interactive atmosphere-ocean coupling. So this leads to the COVID model intercomparison project, COVID-MIP. The protocol and emissions are introduced in this GMD discussion. Is still in discussion, is under review, not published yet, but it is accessible online. So the key goal of this model intercomparison is to answer what is the impact of emission reductions on climate, including the greenhouse gases and aerosols and precursors. and how do different recovery scenarios they designed affect the climate response. One of the scenarios is the fossil stimulus with longer term increase in the fossil emissions. Is actually very fast recovery back to normal fossil emission. And there are also moderate and strong green stimulus with a goal of longer term reduction in fossil emissions. For E3SM participation, so far we only ran simulations to look at the near-term impact of the COVID lockdown emission reductions. The simulations we extended one of the DEC simulations, historical simulations with the SSP 24.5 emissions and forcings to 2020, then start ensemble simulations from this point for two sets. One is with the baseline SSP 2.5, the other with the COVID emission reductions. So the ensemble members are just perturb their initial conditions, very small perturbation. So this slide shows how the aerosols and precursor gases emissions are reduced in a COVID simulation. So the red curve shows the baseline SSP 4.5, and the blue line shows the COVID reduction by species. Black carbon, for example, in panel A here, black carbon and SO2, they have the largest reduction from January 2020 all the way to is revert to the baseline in 2023. So by the end of the 2022, and the greenhouse gases in E3SM simulations, we also follow the protocol to reduce the well-mixed greenhouse gases. However, we didn't prescribe any change in land use, and no changes in ozone or NOx and other ammonium. Some other models with chemistry, they do have those changes as well. So this is one of the key results come out of the paper just published on GRL, Jones et al. Is the summary of initial analysis of the COVID MIP simulations. So what's showing here are 4 panels. A shows the global mean aerosol optical depth in the visible band, and B shows the surface downwelling shortwave radiation, and C shows the global surface air temperature change, and D shows the precipitation change, all compared to between COVID simulation and the baseline. And the horizontal line shows the ensemble mean for individual models, and the shaded colors shows 1 standard deviation. And you also notice that the vertical lines at the beginning shows the mean plus minus 1 standard deviation in year 2020. It's for a better comparison between different models. So all the models shows a reduction in AOD, mostly greater than 1 standard deviation in year 2020. And also shows that the AOD recovers by 2023. That's basically consistent with the prescribed emission reductions. And if you look at the surface downwelling shortwave radiation, there are some positive forcing at the surface in year 2020 to 2021, and start to decrease, change to negative in some models. And the global mean surface air temperature and precipitation, they have, for the ensemble means, they have very small changes and pretty noisy. And oh, by the way, the E3SM model is in the blue line here. And if you look closely, E3SM does show a warming in between 2020 and 2022, and also there's an increase in precipitation. We'll look in more details for E3SM later. And this slide shows the regional changes in aerosol optical depth because the emissions are not uniform. The emissions are not uniform in major source regions, mostly concentrated over Asia. So we would expect that LD change will be most significant in this area. So as indicated in the box, black box in each panel, which represent each individual models. So you see that all the Earth system models, they agree that the largest mean AOD change reduction are in Asia in this box. If we want to look at E3SM, is here in the middle. It does not have a strong AOD reduction compared to some of the other models, as you can see. And also, except for the reduction, there are also patches of AOD increases. Those are most likely due to changes in circulation wind and then cause dust emission changes. And the question is, does the stronger regional AOD reductions have a more significant impact on climate in Asia? So the similar figure as what I just shown, but is for the mean over the Asia box. So if you look at the AOD panel here, there's a strong model agreement, even stronger than the global mean. So over Asia, the regional AOD is decreased immediately, then recovered by year 2023. And the magnitude is almost 3 times stronger than the global mean. And also, if you look at the surface downwinding short wave, the regional, the warming is also about 3 times stronger. And looking at the surface air temperature over Asia, the model ensemble and does indicate a small warming over Asia. But the magnitude is actually smaller than the 1 standard deviation across all the ensemble members for each individual model. And for precipitation, there are even less agreement on the changes. But I want to mention that our E3SM model and Canadian Earth system model do show a strong increase in precipitation over Asia. It's very likely related to strong circulation changes. So for the surface warming, they do have some, there are indeed some very strong regional features, cooling and warming and cooling. For example, there's several models, including E3SM and CESM. They simulate very strong warming over northern Asia. And however, there are also models showing strong cooling there. So it's a very mixed signal from different models. Also for high latitudes, some models shows very strong cooling. Some models shows very strong warming. So especially for the high latitude remote regions, the change in temperature is related not just to radiation change. Very likely the heat transport are very different in different models. And let's take a closer look at the radiation changes. First, the surface downwinding shortwave radiation. So if you focus on the black box for each panel, it's still marked the Asia area. Most of the models do show increased shortwave at the surface, but there are also patches of increases that complicated the response. And also there, if you compare all the different panels, some panels have smaller spatial variability. Those models have much larger ensemble members. For ensemble of 10 models, 10 simulations, the variability is spatial variability is much larger. And also notice that there are also high latitude regions, both Arctic and Antarctic. There are surface warming and cooling in different models. And in particular for E3SM, there are reduced surface shortwave radiation, but also you see warming in the Arctic. That suggests that either long-wave radiation and heat transport are dominant the surface temperature response. So again, so far I've been showing the 2020 to 2024 mean, but there are also inter-annual and seasonal variations. Let me get rid of this. And so dive more into the E3SM model. So we do see different annual changes in AOD cloud drop number and also moisture convergence in different years. Look at the top panels, AOD in different years from 2020 to 2022, and cloud drop number in the middle, and precipitable water at the bottom. There are significant changes in the anthropogenic AOD, and also those red spots showing changes in mostly in natural aerosol dust. And in general, the cloud drop number reduced in the northern hemisphere, which is consistent with aerosol changes, and precipitable water in the northern hemisphere also increased in general, but there are strong shifts and reduction in precipitable water in the tropics as well, indicating some strong, large changes in the moisture convergence and divergence. And this slide shows the clear sky net radiative flux at the TOA at the top, and in the atmosphere and at the surface. So in general, the surface and atmospheric warming is consistent with what we see in the temperature response is consistent with the net radiative forcing. But there are strong regional changes that it's mostly due to moisture change and aerosol change for the especially for the mid latitude. And if we add the cloud effect, looking at all sky radiative fluxes, there are larger spatial variability as expected, because the cloud response are less predictable. So if we compare the surface air temperature change in E3SM and CESM, and also with a simple energy balance model, is just a response to the forcing change. So the E3SM model here does show a slower warming from the beginning of the forcing, but it peaks in 2022 is consistent with the simple energy balance model. However, CESM is different. It has a very fast response in the initial warming, but turns to cooling very soon, even before the end of the aerosol reduction and the greenhouse gas reductions. And for CESM, if you look at the zonal means, the CESM cooling is mostly in the change is in the high latitudes. But in E3SM, if you look at the Arctic temperature response, the warming persists for all 3 years. That's very different between the two models. So precipitation changes are, as you have seen in the global mean responses, they're very different among the different models, and also the regional patterns are quite different as well. For example, all models you see very strong changes in the tropics, which are also consistent with what we see in the radiation and temperature response related to cloud forcing. And there are some signals, for example, E3SM have very strong increase in precipitation over East Asia and South Asia. But there are also some other models showing similar signal, but not across all models. Then if we compare, just look more into the precipitation response in E3SM, the top panels showing here from year 2020 to 2024, the strong signature stands out as the tropical shift in precipitation pattern. It's very likely related to the shift of ITCZ, which is also consistent with temperature change. So the ITCZ, the precipitation shift to the northern hemisphere, where the northern hemisphere is warmer. And then changes from 2020 all the way to 2024 indicates a strong dominant impact of ocean processes. So we'll look more into those changes. Last slide before summary. The comparison of precipitation changes between E3SM and CESM showing some also interesting features and differences between the two models. So first of all, the ITCZ shift in response to the temperature are different in the two models. They're not exactly in phase. And if we compare it to an earlier study by Yang et al. With the EMIB type simulation with fixed SST and CIs, actually our E3SM response in E3SM is in year 2020 is very similar to what in the EMIB CAM5 simulation. And although the CAM5 is the same atmosphere model with CESM, they're very different in the first year even. So that means the ocean in this model probably has a stronger, faster response to the changes. So yeah, just to quickly summarize, we have this COVID MIP has been completed, and E3SM model participated in this activity. And the initial results shows interesting responses in aerosol, radiation, temperature, and precipitation. But they're very much stronger regional responses at shorter timescales. We do have further an ongoing effort in analyze the simulations, especially just with the E3SM and CESM model on the, for example, the atmospheric circulation changes and on the East Asia extreme precipitation in the summer of 2020, and also mechanisms behind the complicated high latitude changes in response to the COVID lockdown, and also the dust life cycle response to the COVID lockdown. And I will just put this final slides for your information. Also, I do want to explicitly thank Sterling, Gio, and Renata for helping on the publishing the E3SM dataset to ESGF. All right, thank you.